Hello again. We don't have more calculations, but I thought it could be nice just to do a quick overview of the results that we have achieved in this long and tedious exercise. So what I'm going to do here is just draw up a little circle with some distribution names. So we have the normal distribution, and we have the gamma distribution, and we have the Weibull distribution, the log normal distribution, and we have the inverse gamma distribution, and the Pareto distribution. And the Pareto distribution. So like a general rule of thumb is that going this way here, the tails become heavier and heavier, but not quite. But you can definitely count on Pareto being one of the heaviest distributions that you will meet out there, and the normal distribution being one of the most light-tailed distributions you will meet out there. So the Pareto distribution is definitely one of those heavy-tailed distributions, and the normal distribution is definitely one of those light-tailed distributions. So let's just take a look at how they compare to each other. So what we know is that the normal distribution has a lighter tail than the gamma distribution, right? However, if we take the tail of a gamma distribution and compare it to the tail of a Weibull distribution, the only quick answer here is it really depends on the parameters, so it's complicated. And it is extremely complicated. So we'll just sum that up in a second on the sidebar here. When we compare the Weibull distribution's tail with the log normal distribution's tail, quite readily it is shown using L'Hopital that the Weibull distribution's tail is lighter. So the Weibull distribution has a lighter tail than the log normal distribution. And when we take the log normal distribution and compare its tail with the inverse gamma distribution's tail, we also see that the log normal distribution has a lighter tail than the inverse gamma distribution's tail. So the last case is the comparison of tails between the inverse gamma distribution and the Pareto distribution. And here again, the verdict is it's complicated. Where we kind of say that if it kind of depends on what gamma is in this distribution compared to alpha in this distribution. So if gamma is greater than alpha, then this is heavier than the Pareto. So then this inverse gamma distribution has a heavier tail than the Pareto distribution. However, if gamma is smaller than alpha, then it has a lighter tail than the Pareto distribution. And if these two are equal, if gamma equals alpha, then their tails are equivalent. So the only thing that we just have to list up before I finish off this thing here is what is the relationship between the gamma distribution and the Weibull distribution's tails. And the case here is that first of all, the first fork in the road is what the value of B is in the Weibull distribution. So depending on if B is smaller than 1 or greater than 1, so if B is strictly smaller than 1, then what we get is the the Weibull distribution is the heaviest, has the heaviest tail, then Weibull heaviest. So you guys know that, this means that the Weibull has the heaviest tail, and if b is greater than 1, then the gamma distribution has the heaviest tail. However, if b is equal to 1, then we have to look at some more cases. So if b is equal to 1, it depends on how beta compares to 1 over a. So we have the case beta smaller than 1 over a, beta greater than 1 over a, and beta equal to 1 over a. So if beta is smaller than 1 over a, then G is the heaviest. The gamma distribution is the heaviest. If beta is greater than 1 over a, then the Weibull distribution is the heaviest. However, if they are equal, then once again, it depends on the values of alpha. So if they are equal, then if alpha is greater than 1, then the gamma distribution has the heaviest tail. However, if alpha is smaller than 1, then the Weibull distribution has the heaviest tail. And if alpha is equal to 1, then we are able to show that then actually the gamma and the Weibull distribution are completely identical to each other in density. So that just means that then there is no difference between these two distributions. So you can see that when we say it's complicated, we really mean that it's complicated. So just remember this. It can come in handy sometimes if you need to, do some intuitive discussions in your answers for the exam. Then it can come in handy just to remember stuff like, oh, the log normal distribution has a heavier tail than the normal distribution, and so on and so on. So remember this.